Welcome back, as we continue with functors, applicatives, and monoids. A functor is anything that can be mapped over by a function using fmap. Examples of functions include lists, trees, maybe, I/O, and even functions. If you remember the map function in Scheme, it takes a function and maps it over a functor, such as a list. A common analogy for functors is the box analogy. If we imagine a functor as the contents of a box, we can imagine telling a function to apply to everything that's in the box. In the case of maybe, see the example on the right, maybe there is something in the box to apply the function to, and maybe there isn't. If there is not, it does nothing. For a list, there are a bunch of items in the box, and the function is applied to all of them. This box analogy doesn't work for everything, but it is a good way to gain a basic comprehension of what a functor is. Functors are things that have fmap defined for them. Fmap lifts functions to operate on functors. A function that normally takes an integer as a parameter can be lifted by fmap to take a functor, like an array of ints, as a parameter. Applicatives are functors on steroids. They can be mapped over by functions that take multiple parameters. When we do this, we wind up with functors with functions inside. Functors have one function fmap. There are two functions for applicatives, pure, and that little symbol over there pronounced applied over. Pure boxes something up, turning a value or a function into a functor. As you can see in the top example there on the right, we have a class constraint that all factors must first be functors. There's a function application symbol in the bottom example that is a symbol that Haskell defines in order to chain things together into the next applicative style. The applicative style mentioned on the previous slide is shown in the upper right function as a list of functions applied over three sets of functors with values being passed from list to list. Examples of applicatives are maybe, lists, I/O, and functions. In short, applicatives are functors on steroids that allow chaining, as seen above. Alright, now we'll get into when you would use different examples of applicatives. Maybe could be used for a computation that could fail. Maybe you have a value, and maybe there will not be a value at all. Maybe would not return an error in this situation. Either is similar, but instead of looking for a value or no value, it has left and right logging, with left representing failure and right representing success. This can be used when some values will return true and others will return false. List is very useful for non-deterministic computation. You could use list applicatives for calculating the outcome of all possible input values by including them all as a list. I/O can be thought of as a function with side effects. Usually Haskell is a very pure as far as it being a functional programming language. However, at some point you need side effects because you need input from a user. I/O lets us bundle all of those side effects neatly into one class type, I/O. Lastly, functions can be thought of as values that have not been calculated yet, also known as non-deterministic values. They can be thought of as whatever they will return, such as the value that is not yet computed. As the last part of the presentation, we will talk about monoids. Monoids, like many other things we have described so far, have their behavior defined for them. They are binary, meaning they can take two parameters and return one of the same type as the input. They have to have an ID value. For example, the plus ID is 0 and the multiplication ID is 1. What associativity means in terms of monoids is that it doesn't matter the order that the behaviors are written. If you take our example on the right there, any of those definitions could be nested in any order and it would function the same. Empty is basically just the ID. Mappend is for appending lists. Anything else it's using is putting two things together more than appending onto one. And mcumcat is what you use for folding monoids. It's not often defined and is often used with a default explanation. Please continue to our next and final video to discuss monads, the most important part of this series.